Okay, so it's Boost serialization. Every time I look at the code, I mean, all the heck is it working, you know? And some corners of Boost.PROTO is basically the same. What the heck I'm looking at? So, okay, let's put some batteries inside this. Okay, great. So I think everybody's still there. So on to the last part of these sessions. So we speak about that. So, okay, so the question is, I got all this nice looking stuff. We will see another more complete example of what we can do just afterward with just a screen too, so you can see what we can do, okay? Oh, and I probably need to put my microphone on. So, last session of this stuff. So, as I said, so we have all those nice tools, okay? We just played a very, very few bit with. I will go over an example just after that, so we can see what kind of really kooky stuff we can do with it. So there is traps, okay? And those traps, for some are actually okay, and for some are actually real traps you don't see coming. So basically you have combination of expression templates and auto. Function returning sub-expression that may or may not contain temporary terminals. And of course compilation times, okay? Because, well, it's rather, as you could have, so it's a bit easy. So what's the deal with auto? And by auto, I mean actually all the automatic type deduction into the language, including templates, okay? So look at the code I wrote there. You have, let's say you have an array classes, which is actually a expression templates terminal, okay? So you have some stuff, and you say z auto z equal x plus y times 3. Question is, what's the type of z? We saw it. It's not an array. It's whatever the underlying expression template systems give you as a type for this kind of expression. Okay, so this assert on is same should have been a static assert, will fail because it's not an array. Well, actually, logically it is. It's like an array, except it's not physically. Okay, and auto doesn't carry this information. So that's something you can actually live with. It's not very, very, you know, limiting. Where it poses more issues is there. So let's have a look at the function bad double. Question is, why is it bad? It's bad with respect to usage with expression templates, of course. What happens if x is some expression types? So x is, for example, let's take a simple example. Let's say it's our binary expr we saw a bit before. And we return x plus x, which will be a binary expr of plus between the type of x and the type of x, which is clearly not t. It's not t, it's something else. And you don't really want to care about that. Bad double works if you pass it to regular types. Okay? Well, a regular types that which is the output types is the same as the input types when you call plus, but you see what I mean. And what you should be doing is what Godable does. You just return auto. And then you get the correct types. I don't say you get the correct results. You get the correct types. More on that. And the other issue is that sometimes you do something which is completely, you know, logical, but will lead to crappy performances. So let's look at foo. So you learn your lesson and you return auto, okay? But something is still wrong there. What if you pass the regular types? You compute x plus x once, put it into d, and compute d times d. Okay? So now imagine that plus for your types is very costly, okay, for whatever reasons. And you pass an expression templates expression as x. Okay, so you will build the expression x plus x, and you store it into d as a sub-expression. And you put it 2 times, and you end up with the expression which is x plus x times x plus x. And you do twice the computation of x plus x. Because you store it into auto. So you have to be careful with automatic type deduction and expression templates because the language does what it should be doing. I give you the type of the stuff you ask it for. What do you want me to do anyway? Okay? So you have to be careful with that. So I don't know. Different solutions exist, actually. So either you know what you're doing, which probably means you are not into a very generic context, and so you just put the damn actual terminal type where they should be being done, okay? Except that means that you cannot write functions that just take whatever and do whatever. So we ended up with this viral contamination application of auto everywhere, which solves the outgoing issues, but doesn't solve the issues inside. So some libraries based on expression templates provide a function or meta function that is roughly called value of or terminal from, something like this. Take an expression and give you the type of the terminal that should be able to contain it. And so you can locally decide, but you are still into a generic context. And the other stuff we'll speak about later is there is a proposal Herb Sutter, Peter Goshling, and myself wrote, which is basically provide a way to overload auto for given types. More on this later. So it's not trivial. You have to be careful as soon as you have automatic type deduction and expression template in the same box. Okay? So that's the most complicated stuff. You have to be careful with this. It's bad somehow because we all really love auto, but not in this case. Okay. Other issues is this, what I call the sub-expression issue. I spent quite a lot of time on this trying to fix it properly. Okay, we'll speak more about that later. But one trivial stuff is usually as soon as your terminal is bigger than a simple value, that is a table or something that allocates memory, you want to store your sub-expression by reference because you don't want to copy your terminals. Okay. Wait, okay, fine. But what if I do this? So I take something as x, could be an expression, and for whatever reason I know that I need to evaluate right now, because I read the slide just before, I will evaluate this sum of 2 times x plus 3 into my terminal, which is array. So this allocates some memory and do the operation inside. Okay, and what I return is the expressions 2 times t minus 1 over t, which is the reason I evaluated everything in an array because t was twice into the sub-expression. Okay, so t got some memory allocated. What should I do for this code to work when I return 2 times t minus 1 over t? What happens if I store everything by copy inside my expression? I will probably duplicate the memory of t far too much. Probably 3 times, okay? Because you will copy it into the divisions, copy it into the multiplications, 4 times, and copy both again into the minus. So if array is like 1 gigabyte, it's not gonna fly, okay? Okay, so just take everything by reference, right? So what happens? Well, bad story for you. I will have a reference to t in my 1 over t, same for 2 times t, and I'll go out of the function and t get disallocated, and I got nice dending references to memory that's not there anymore. Crap. So, what should we do there? What could be the solution? Boost.PROTO is very adamant on this. By default, everything in Boost.PROTO is taken by reference because most of the time, but I disagree with that. Sorry, Eric. That's the correct thing to do. And if you want to do this, you have to call a function called Boost.DeepCopy, which, as the name implies, perform a recursive copy of everything in the tree into another one. So it assures that everything outside is still there. But of course, it's very costly. And as again, that was it's C++ 98, so we didn't have move semantics. So one way to do this is, if I could find a way to use move semantic into the situation so I can decide if the stuff that's coming in has to be copied or not. And so I decide which kind of storage I need to have, could be handy. But it's not that trivial. So this kind of stuff, just for the gigs, okay, this exact same kind of bug took us something like 2 months and a half, 3 people, okay, to find it. When you saw it, it's obviously obvious that you did something wrong. But I can tell you that when you are writing your codes and everything works, because of course the test pass. And why does the test pass? Because well, you get flushed by the inlining of the compiler when you in release mode, and everything gets inline, and the reference never exists actually. And as soon as you go somewhere else, and the guy is actually using your code in the client and compiles in a low level of optimization, everything blows up because the references are there and not inline anymore. So that's a very crooked bug. Okay, don't do that, or do it correctly. And the other problem is compilation time. So if you do a small-scale DSL like the first part, probably fast enough for what you want to do. And the problem is that you remember these symbol names that grows up exponentially. Oh, not exponentially. I mean, probably, oh, well, far too fast. Okay. And those symbol names, that's something I suspected, and Todd Veldhuizen actually suspected too, and actually, I mean, demonstrated that it was the case. First sources of compile time issues with DSLs is symbol names. Because contrary to regular codes, they just takes a humongous amount of space compared to what they encode. And the other problem with Boost.PROTO and other similar systems is the complexity of the transform you apply on the tree. Not the complexity of what you write in the Boost.PROTO transform, what it actually does. And how you have to actually explain what it should be doing in terms of types computation. So the solution is simple. It's do the simplest version of expression template you need. If it doesn't need the Boost.PROTO full-fledged stuff, don't use it. Take it like a grown-up and write your small-scale stuff. But if you need something more complex, you probably need Boost.PROTO. Well, good luck. Back in the day, the first time I used Boost.PROTO, it was in 2003. Oh, no, 6. No, 3. Or 3 or 6, I don't remember. Somewhere, 2005. I was working on a very, very, very small system with like 1 GB of RAM and mostly 1 GHz of CPU power. And I was trying to write Boost.PROTO transforms that transform, you know, chains of matrix multiplication into the optimal forms, okay? And the joke was, as soon as I had more than 5 matrices into my expressions, I could launch the compilation at 11, go to lunch, go back at 1, and then I get the result. So, well. So actually the real problem is that we force the compiler to do its damn job at least 3 times. So what it could be cool is if we could have a language support to say, okay, you take this expression and please give me this tree and I need it for doing something else. And the compiler just, okay, this is a tree I just passed, so have it. Could be far, far, far more efficient. Well, that's a bit complicated. And one thing we cross-discovered, so me, Todd Veldhuizen, Louis, for completely other stuff, is that you can actually use C++14 lambda in a perverse way to write something that looks like expression templates. I will show you that a bit later. So compilation time is probably currently the most biggest problem, and it's very complicated to get something that compiles fast all the time. Okay, so that's a big problem. So before going to the next level stuff, let's have a look at what kind of cookie thingy we can actually do with Proto. I won't go into the details just so you can skim and you can actually look at the complete code into the GitHub. So that's something I was doing when I was making a 5-hour tutorial on Proto. And you actually have to write it by hand from scratch. So this is what I want to be doing, okay? I have a bunch of terminals called X, Y, Z, and so on that represent arbitrary abstract variables. And you can use them to actually build arbitrary analytical functions with multiple variables, okay? So you can actually do stuff like this. Okay, so you can write that and pass it 2 variables, and you will compute the function on the 2 points for X and Y. And what we wanted to be doing is, I wanted to be able to say, oh, I have X times Y, compute the derivative of this function with respect to X, and give me a function I can call with some values. So I can evaluate the derivative of this function at this point. And once you do this, what you want to do is, what about having the nth derivative, which is basically the recursive application of the derivation function n times, okay? And so you can actually write code like this. So you can also have support for cos and sine, okay? And it just works. And how does it work? Well, when you compute the derivative of a function, what do you get as a result? A function. So what we do is we take the proto tree representing your initial functions, and the transform we write just takes the function and say, oh, I have a plus node. I need to derivate it. And the derivation of plus a plus b is derivative of a plus derivative of b. So I compute the two derivatives of my children, and I build a new tree with this. And you just enumerate all the derivation rules for plus, minus, divisions, and so on and so on. And as the output you get is a tree in the same domain than the one before, you can just pass values for your variable, and you just compute. And all those derivatives computation are done at compile time, actually. So you get a new analytical pre-inlined functions directly at compile time. Okay? So you can have a look, I mean, really whenever you want, but this is the main idea. So we have a grammar. That's just something I didn't speak about. It's what we call a switch grammar. The issue with OR is that it's linear time to find the rules you want to match. Take the first one, and then the second one, and so on and so on. When you have more like, I don't know, between 8 and 10 rules, it starts to be very, very slow to compile. And then we switch with something which is called proto switch. It says, I'm taking a structure which contains all the cases I care about. And these cases can be declared externally to the grammar. So the first case is if it's a terminal. Okay, so it's a bit more complex than what we saw for terminal, okay? This is a terminal if it's a terminal of something, and only if the value of the terminal is convertible to bool, which means bool and floats, basically, okay? So we can write that we have a proto if we can use for taking decisions. And then we say, yeah, I can negate, I can do plus, I can do minus, okay, and so on, and so on, and so on. Okay. So it's like OR, except it's done externally. And as I say, you can do function. So how do you do functions? You need a type, which will be a tag, and say, oh, I am a cosinus node. Okay, so that's the name of, that's the reason to have this kind of cos tag. And we say I can compute cos by taking some value and calling std cos, for example. Same stuff for sin. And what you write is something like this ugly stuff. You say I have a function called cos, taking something, arg0, and what I return is an expression of cos tag as a tag that contains arg0 by reference to a constant. And we just call this cref stuff to store it. Okay? So we have this make_expr function in Proto that just build an arbitrary tree with an arbitrary tag and storing every child arbitrarily as a value or as a reference or a reference to const. Okay? So when you call a function, you just say, okay, I'm just giving you the node with the correct tag and whatever children. Okay? That's basically what the operator does, except it's hidden. And same for sinus. And then we do the grammar for cos. When I have a cos, I mean that I have a unary expression of cos tag applied to something. And when I match that, I have a cos. Okay. Oh, and we may want to know what I do to evaluate them, because all the other operators, we know that we have this otherwise default mod. And for cosinus and sinus, what I do is, whenever I have an expression of cos tag, I evaluate my child, and I pass it to compute cos. So pardon my French, like they say, but it's not complex. It's complicated because you have a lot of bookkeeping to do. But every of these bookkeeping are rather simple, just that you have to go through all those hoops. So when you write it once, I mean, it starts becoming, you know, some kind of reflex, okay? But you have to go through this once, actually. Okay, fine. So this is enough for building, oh no, it's not enough actually, but this will help us building the regular expression. So what we do is that we have an expression types like we saw with the domain and so on, that just do whatever, except we can call with up to 3 variables. So we have 3 operators function call with 1, 2, 3 values. And what we do is that we store everything into an array, and we pass this array as a second parameter to the evaluation. And we will have access to this array through the proto transform as a state. We can read and write from and to. Okay? That's easy. And evaluate, where is it? Evaluate, just say, okay. It's the same stuff. It uses cases. It's a switch over each cases. I will go on that a bit. I mean, if I'm a terminal of the proper type, I'm just giving you my value, classical. Okay. And if not, the default case is just the default case we saw before. And now the question is, how this derivate stuff works? Well, that's a bit more complicated, but not much. Still again, we have a switch-based grammar, but we don't have any default. So what happens when, or I will keep that one for later. Yeah, what happens if I want to derivate minus x? Whenever I have minus x, I build a node, which is minus something, with the derivation of my children. Okay. Functional make negate of the derivative of my child. And I pass that to another function which is called simplify. I will go on that a bit later. But what will simplify does? Well, let's say you have x times x times x. And you want to compute the second derivative of that. You will end up with something like x plus x times x plus x plus x plus x. You will have a very complex tree because everything gets, you know, unpacked when you do the derivation. And you want to simplify that to be x plus 2 times x and so on and so on. So simplify just limits the size of the tree. And we just enumerate all the cases of the derivatives. Plus is a plus between the derivatives, same for minus. Multiply is a bit more complex, but because the rules is more complex. And so on. Well, sorry, divide is the worst, actually. I think it took me 15 minutes to get it right, but, well, whatever. And cos is basically minus sin, and sin is basically minus cos. And what does nth derivative does? It just calls derivative on itself n times. Okay. And what happens when I want to derivate a terminal? How much cases do I have? If it's a constant, I get 0. Oh, wait, no. If I derive against x and it's not x, it's 0, including the constant. So what we do is, if I have a constant, I just return 0. Okay. If I have a constant like constant 0, I just return constant 0. Okay. And if I have a variable, x, y, z, each variable has an index, 0, 1, 2, and you derivate against another one. So if the value of the terminal I am looking at is the same as the one I'm derivating against, so I have an x and I derive against x, then I return 1. If not, I return 0. Well, when it written is trivial. Writing it is another issue. And so that's what? That's probably, well, this one is a bit big, but it's less than, let's say, it's about, I would say, a bit less than 1,000 lines. Okay, probably around 600 or something. Nothing is actually complicated. It's more like syntax issues and getting the algorithm right. And you get this derivative stuff working. Okay. That just works. And when you look at the generated code, you just get whatever you need. And I don't think you can get a better interface than that in terms of clarity of what you want to be doing. Okay. Well, we can do stuff like this. You can actually do far more. So Boost MSM is actually something that builds a state machine from operator overloading and generates the perfect automaton for doing it, which is quite a bit impressive. There is a bunch of linear algebra matrices-based expression templates. They are all get very nice features. I mean, you can basically do whatever. So the question is, I mean, it's like in Spider-Man, you know, like with great power comes great responsibilities. And what do you really want to do with it? Okay. Sometimes you should be just not doing it because you may find a far simpler design without any lazy stuff inside if you can't do it. Okay. But sometimes you really want to have this. Okay. So what are the limitations? And we saw, and there is some work being done, try to find this. So the other one, okay. So first question is, should I still doing this? As I say, we have smooth semantic, we have copy additions, we have a far more better compiler than before. And yes, most of the time, if you are only looking at performances, it's probably not what you really want to do, because the benefits risk analysis is not in favor of this kind of stuff. But what you really want to do is write intentional code, and that you cannot do using the compiler. So you want to make your library as intentional as possible, and expression template is just the right tool for that. You can extract information the compiler can't even see, and you can use them at compile time to decide how to write your code and how to generate the stuff. And you can actually rise and reap benefit from a lot of very, very abstract, high-level optimization opportunities. I was speaking in the break about the fact that we can actually write a signal processing library when you have signal and you have noise classes, and you know that if you want to convolute a signal with a noise, which is white, you don't have to do your full convolution, probably have a simpler algorithms, okay? And so you can detect that and generate the proper algorithm. But the compiler can't read that. I mean, it's human-level information, okay? So you want to perform domain-specific optimization. Because if you just want to generate a perfect for loop with vectorization and whatnot, it's probably overkill, because most of the compiler probably do it right now, except for some kind of cases when you need this. But as soon as you want to reap benefit from high-level optimization, that's what you will be seeking with expression templates. So I'm coming back to auto. So I was speaking about N4035s. So the idea is to be able to write that. So you have a product expert, which is some kind of, you know, lazy node like we wrote that captures matrix product, okay? And what we want to say is that, oh, wait, if you use auto on that, I don't want you to give me product expert, give me matrix instead. So this notation just say, whenever you use auto on that, give me this instead. That means that you can actually write code like this. So this auto z equal a times b, uses using auto equal notation, and that's basically matrix z equal a times b, which is exactly what you may intuitively want. But if you really, really want the lazy expression, you can just write explicit auto w equal a times b, and you get the real auto behaviors. Okay, so that's something we are still working on it. It gets somehow well received, so we have still hope to get through. But that's some interesting text. And one thing is that, okay, it's useful for expression templates, but not only. It's actually useful for any kind of proxy types, where you don't really want to store the proxy type in auto, but the real actual types behind. So that's something we can actually work with. It's more general than expression templates. And my secret agenda is trying to find the biggest amount of generically applicable suggestions to the languages, so some of the problems are solved, and I can use it into expression templates related problems. Okay, just cut that at the video, please. So another stuff I tried to do recently is so for the people that doesn't know, so I mentored with Dion for his work on Boost.HANA for 2 years now, and looking at what we did in HANA, I will say, okay, we have all these cool C++14 based tricks that give us a very lightweight and very interesting way to write stuff like tuple and things like this. And shouldn't we be using these kind of tricks to rewrite something which looks like Boost.PROTO, except probably compiled faster and with less code? Okay, so I started working on that. And the idea was to do what I now call, well, Edouard is not there, but with Edouard, again, we have this term we coined recently, which is we want to have a sustainable library. Sustainable library means that it's easy to use for the users. If not, you kind of fail at doing it, okay? But the inside of the library is also simple to look at and understand. Because you don't really want to have a language lawyers, like Björn said, to explain you what's going on into the library. This need actually raised from the fact that when you work with people with different level of C++ knowledge, and your job is actually, like me, writing libraries, it's very complex to get everybody on the same level of stuff. So the simplest code we write at the library level, as a developer of a library, is the best it is, as soon as we keep the same level of usability. So we want it to be sustainable. So the trick is to say, we use what I call symbol name compression to fasten compile times by reducing the amount of text into the symbol name of the expression. And this is done by actually using C++ polymorphic lambdas to generate the expression node. So I will just show you that. And so it's still not complete. I still have to work on the how to actually add semantic to the stuff. But the idea is this one. Okay, where is it? So just have a look at what's going on. So we have an expression class. Okay, so it's a bit rough. Okay, but the idea is that we have an expression class that contains a tree as a type, like before. But this tree is actually not another expression, not another classes which is recursive or whatever. It's actually, and I think we saw it there, the tree is actually a lambda. And what does this lambda do? Well, it takes a visitor as a parameter, and the visitor will be applied on whatever the lambda contains. Okay? And how is this lambda built? So this is a bit of, okay, this is basically what happens there. So I have a bunch of types, values I want to put as the children of my expression. And what I do is I build this lambda there, tree, which is taking a visitor, v. And what does it do? Well, whenever you pass a visitor to my lambda, I call my visitor function call operator on what? On a value which is the tag of the expression I'm currently building, plus, minus, etc., and all the children of this that get captured by value automatically. Okay? And I just build an expr of type of this tree. Okay? So what I say is that a subtree is no more than a closure that will accept the visitor which is coming from the transform when I go down the tree. And at every level of this, I know where I am because I call the visitor with my tag. So the visitor knows what's going on. Okay? It may not care about my tag, but if it does, it knows who I am. And I can match on that. And surprisingly, it works. And by surprisingly, I mean really surprisingly. And one interesting point is this is the kind of type you get. Is it? Oh, why? I don't have any more. Okay, sorry for that. Is the zoom okay for the text or not? Maybe I can actually probably get better. 5 seconds. Okay. Oh well. Where is it? Look at that. That's the output. I just build an expression, and I print the type name, okay, using demangle, okay. And that's compiled with Visual Studio 2015 with C++14 support. So it actually compiles on Visual Studio. So I have an expr. Look at that. I have an expr that contains what? A lambda of this type, lambda underscore AAF9 and blah, 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 which is probably a hash or something. Can I actually get everything? Okay, I just rerun it, okay. So this lambda underscore 32 characters, which probably a SHA1 or some other hash. So that's basically the type automatically generated by the compiler for the lambda. And good news, everyone, on Visual Studio, it's a fixed size identifiers. The first one is A plus B. The second one, same sign, is A plus B plus A plus B, and so on. And the third one is A plus B plus A plus B plus A plus B plus A plus B. And the last one is that again with itself. So it's like about 16 symbols. And it's still the same size. Roughly 40 characters or something. Okay. Well, it's not demandable. I mean, at the very beginning, when I had a bug somewhere inside the lambda, you got message like, OK, I cannot find this and this in lambda 1, 2, 3, 4, 5, 6. OK, great. So don't do bugs. OK, no, I'm joking. So I think that Joel de Guzman-Luis, I think, had the exact same idea for Spirit Tree, and he discarded it because of the difficulty of debugging. I'm still thinking that the benefits outweigh the risk, because we basically get constant time, compilation time with respect to the complexity of the tree. Yes? I was going on that. So that's true on MSVC. On the other compilers, you still carry the name of the function the lambda was built into the name. So it's a bit longer. And if you do the tricks on GCC or Clang, you see that the symbol names grow linearly, but by probably 8 or 10 characters at a time, instead of the huge mess you get with the regular one. So I still think that as GCC and Clang compile faster than Visual Studio, one in the others is basically as fast on both sides. Now, I don't know if there is anybody from GCC or Clang there, or will watch the video. Please do whatever MSVC does while they name their lambdas. Please, thank you. So that's probably the best idea the Visual Studio implementers had on this point. That's a very, very interesting techniques. And the other funky stuff is that we also find a way to say, OK, now I know if I need to copy or not. So by default, this library takes everything by value, by reference, sorry, except when he knows it's dangerous. And so what we did is an actual, that I actually have to thank Louis for that, because I was swamped by a lot of time in this. So what we do is this kind of thingy. So when should I store a sub-expression as a value or not? Well, if the stuff you give me is a value, that probably means that its lifetime is bigger than the lifetime of the expression, so I will just take a reference to it. And if not, if it's a value, I will save it into a value by doing a copy, or well, sorry, by doing a move assignment or something. So that's what the storage type T does. I mean, if I have a value, I just decay everything. If not, I'm keeping it as a reference. Except there is a problem. You have no way, when you define a lambda, to select for each captures which one will be stored in a way or another. I think that's fixed in 17 or something, but it's still limited. So what we do is, it's like pool, you know, you cannot go to the OR directly, so you do a bend, you know. So what we do is we build a lambda that captures everything by reference, this array type stuff. And inside, you build a regular structure that uses storage types on the types of whatever it's captured, okay, to decide how to store it. And you just forward the value through it. And this lambda just returns a new node. And what you return is an expression containing this node. So you have a lambda building a small-scale structures from the inside that has access to everything from outside by the capture, which means that it's not in its own type. There is no template child something there. That's where the magic is. There is no relationship between the node name and the whatever contents of the child. And what I learned this evening is that you can actually put a struct there, inside, locally inside the function. I didn't know that. So you do this, and you can actually change whatever you do this. So you can do for 1, you can do it for 2, or you can do it for 3, and so on. And you can, when you have too much, you can just put everything into a tuple and sleep on it. Okay. And you can forward precisely everything the way you want into each sub-element of the tree. And so how does this? I will screw myself by computing something in a temporary, in a function, and I will get a dangling reference get solved. It gets solved in a way I will call which is natural. What is a function? Okay. That's a very rough example, but this is what we are doing there. Is let's say that track is something that is costly to do. Okay, that's our local value that may contain a pointer to something. Well, if you want it to be copied into your tree, you just move it inside. Which is something which look like something makes sense in the language itself. Even if it was not expression template. Okay, I have something there, I want to move it into the outside. I don't want to copy it because I know it will die. Okay, so you just use move whenever it makes sense. So you doesn't have to rely on the knowledge of what is going on into the expression template system if I put this there. Well, just move it and it will do what you want to do. Okay, and if you don't move it, it will blow up. So just move it. So the only limitation of that is that you have X and you want to put it twice into the same expressions. You cannot move it twice. So you probably want to make a copy first and copy the other one or something like this. But that's the only weak points we found of these techniques. And the rest just works perfectly. Just copy if you want to copy and move if you want to move, and everything is logical as if it was regular code. And so the example actually does this. You see, so I have f of copy, f of f, f of f of f, and so on. And we take care about how much move and copy we does. And actually, we do the exact amount of move and no copies each time. So we know that we did the correct thing. So we're still working on that. It's somewhere on GitHub on my account. It's not complete yet, but trying to get something done with this. I got rough compilation time numbers. It's far better. Up to 2 to 3 times faster. There are still some crooked cases where it just blows up, but it looks nice. So probably more on that later. So, but let's go radical. What if you can actually change your languages so it makes sense to write expression template as a first-class citizens? So if you look at other languages, like Tempaltes Haskell or MetaOCaml, there are 2 functional languages with sort of supports for introspections. They have a concept of code fragment. A code fragment is a piece of code in a variable. Okay, and you can create some. You can build a bigger one by concatenating those code fragments. And when you're happy with it, you can just bang it and you get the value. Okay, so that's the example I got there with the, that's MetaOCaml. So I just built a code containing 1 plus 2. And the type of this is a code returning an int. So that's this dot bracket stuff that do this. You have a dot tilde that say, take a piece of code and expand it inside another one. Okay, so you can combine piece of code. And when you do dot bang, it takes a fragment of the code and it just compiles it and gives you the result at runtime. Okay. So the idea is, can I actually do something like this in C++, and does it make sense? Okay, actually. And how can we do that properly? That's an open problem. I don't know how to do this. Volunteers welcomed. The other idea is that we have size off, we have Decal type. What about having an IST off, take an arbitrary expression and give you the tree and do something with it? But the problem is, how do you want to use that to pass the lazy version of an expression to a function without having to write f of IST off? And that quickly escalates into, oh, that means that I need to write f of lazy t or some stuff like this, and it starts to be ugly. Okay, so that's not that trivial, actually. So let's conclude on that. So was this headache worth it? Okay. So what did we learn, actually? So expression templates, we can actually write, the main stuff we have to remember is that we are not only there for performances. That's a side effect. We use expression templates to build intentional code with code clarity as a first goal, okay? We saw that if you really want it, you can actually write a very small scale handmade expression template engine for very, very limited scope. And if not, you have tools like Boost.PROTO that actually simplify such an idiom by providing all the boilerplates already there. And we have some gotchas, especially with automatic type deductions and move semantics. You have to be careful, which probably means that the tools has to be updated, like we said. So what to do? So you are designing a library. That's the main first point. And see if your design of your library can actually be turned into the design of a language more than a library. And if yes, then you can actually play with expression template as a way to increase the code intentionality. That's very important. So the library should be as intuitive as possible, and expression templates help you doing this. And then, actually, you can rely on tools like Boost.PROTO or stuff. You can actually see, I mean, Proto is called Proto because it helps you do prototypes, okay? So prototypes using Proto, see what kind of feelings you want to give to your library, and then fine-tune it. And if it doesn't work, just complain to your favorite compiler vendors, okay? So that's what we want to do. We want to be, we have to move, expression template as a technique has to move from, oh yeah, that's this stuff people does when they handle big arrays. Okay, no, that's not just that. It's the only way we have to build libraries with a high level of intentionality that still give us the opportunity to get cross-function or cross-expression optimization at a very high level. Because we have everything under the eyes and we can take the decision about what is important at this level of optimization. So that's what we really want to do. So as a closing point, I want to thank a lot of people. So Joy Guzman, which is probably the one guy that wrote this Lambda DSL stuff first before me. I don't remember, but I remember discussing it with it at some point. Louis for fixing my crappy implementation of the same concept. Eric Nibler for Boost.PROTO, which is actually a great piece of code, okay? And Herb and Peter for the conjoint what we work on 4035. So thank you for your attention. I hope I didn't kill too much people, okay? Well, John say I can kill 10% of the audience, so I'm probably okay. If you have any question, I would gladly answer, and thanks again for your attention. Yes. Okay, so the question is, I have the choice between using Boost.PROTO and doing the old-fashioned way by doing it by hand. What should be the choice? When should I choose? From experience, I would say, as soon as you have, let's say, a decent set of functional operators, like more than 3 or 4, I don't know, very, very small numbers, you really don't want to get all the boilerplates done. That's very time-consuming, and you will get it wrong. So as soon as you need a large selection of operators, functions, Boost.PROTO everything is just there. The cool stuff with Boost.PROTO is that you can also prototype quickly something without getting any of the grammar or transform stuff. Just play with the syntax. Look what this expression tree looks like, so you can see if you can actually manage to process it easily. And when you are set on your syntax and grammar, well, after you finish the work with Boost.PROTO, so you know what you should be putting into your end fashion stuff. We had this discussion recurrently, with Eric. He said, okay, I did that, but I could have been doing the other way around. Yeah, but you know that you could do it now because you played with the stuff. So sometimes you just play with Proto in what I call the immediate mode. You just write stuff with operators and see what's going on. And when you know exactly what your language should look like and what the logical for transformation is, just write it by hand. But sometimes it's so much easier than say, okay, I will just keep Proto because I need a special semantic. I need to have multiple transforms that do this and that. I need to regenerate a tree from a tree from a tree and so on. And you don't really want to do this by hand. So either you have a very small amount of stuff, or the transform is very trivial, and then you do it by hand. And if not, I would just say go with Boost.PROTO or whatever similar tools. But you need to be able to say something like, well, now I know what to do. And playing with Boost.PROTO is often enough because you just play with the stuff and you see, okay, I should be doing this because the tree is this way, and I can process it. But I mean, we are living with Boost.PROTO in half a dozen of library, and we are just now slowly moving to removing proto and doing it by hand because we know where the spots are now. But it took us years to do this because it was just there working. Compile time was okay, so just let it there. Other question? Okay. So they are free to go, I guess. Thank you again.